Yeah. Yeah, that stuff came in. So, all right, let's see. Theorem here. Let's start off with a theorem. So this is theorem 10.7, and the parametric form of the derivative. So yesterday we did figuring out parametric equations, how to change them into parametric equations from rectangular equations, or going from parametric to rectangular. We talked about that. And then we did a little bit of graphing, but we didn't do anything related to calculus in a sense, because we never took any derivatives for it. So we are going to talk about derivatives today, what they look like and stuff like that. And they're not like really difficult. It's kind of like a formula. You know the formula, you can do the work. So it starts off saying that if a smooth curve C, so it's just capital C, is given by the equations x equal to f of t and y equal to g of t. So again, that means that they're parametric, right? Then the slope of the curve C at x comma y is, and here's your definition. So dy dx is equal to, so they write it the same way, but on top you're going to do dy dt, and you're going to divide it by dx dt. So on top you do the derivative of your y function, and on the bottom you do your derivative of your x function. Like individually, not like as a whole. But you're going to literally just get y and take a derivative of it. That's what you put on top. You get your x function, take a derivative of that, you put it on the bottom. And that's how you find your slope. Yeah, simplify after that and you'll be good. Now, one thing that they always want to make sure that you guys are aware of is that your derivative for x should not equal to 0, right? Because or else you're dividing by 0, so that's not a good thing. Seem easy enough, hopefully? All right. Now there is a second derivative which looks kind of weird, but we'll work through it so you can see. But that's something else you just want to memorize. Or I mean, I guess you could derive it yourself, but usually it's easier to memorize it. So we're going to find dy dx for the curve given by and here's the function they're giving us, x equal to sine of t and y equal to cosine of t. So those are our two functions, x and y, and they want us to find dy dx. So I'm just going to write down the definition again, just for the sake of having it there. So there's dy dt, and here's dx dt. So the derivative of y with respect to t. So what's the derivative of cosine of t? Yeah, negative sine of t, right? What's the derivative of sine of t? That's cosine of t. So if I simplify this, my answer is negative tangent of t. And there's my answer for this problem. Notice it's just based on knowing the formula. You know the formula, you should be able to do the work. Okay? Now, let me write down second order derivatives. Yeah, those are famous last words, right? That was easy. So second order derivatives. So second order, there's also third order derivatives and stuff, but usually the second order is as far as they go if they're going to go further. So d squared y dx squared. Okay, so the second order derivative. What that basically means is to take a derivative of a derivative, right? That's what that means, to take a derivative of a derivative, right? Well, the derivative of dy dt over dx dt, because that's the definition of it, right? That's what dy dx is in parametric form. It's dy dt over dx dt. Well, if I do that, then I can actually multiply the ddx to the numerator. So it's going to look like this. ddx of dy dt divided by dx dt. Do what? Why do I multiply it in? Well, I'm trying to show you the definition, so I'm deriving it. I'm going through the process so you can see the beginning to the end and what you're supposed to know by the end of the process. Then you'll say, oh, so d squared y dx squared is... So we're just working through it right now. So we just started off with the derivative ddx of dy dx. That's what the second derivative means, right? We wrote the definition of dy dx, that's dy dt dx dt, and then I got the ddx and multiplied it to the numerator, okay? And now I'm going to do a little switch. I'm going to get the dx on the bottom of the numerator portion and the dt on the other bottom, and I'm going to flip them, okay? I'm just going to move them, because this is multiplication, right? So I can kind of move them around however I want. So this comes out to d dt of dy dx over dx dt. That is your definition for the second derivative. Okay? The way I remember it, when I think about it, is this. The first and the second derivative always get divided by dx dt. Notice the first derivative right here, in the definition, it has a dx dt on the bottom, right? So does the second derivative. So that's something they have in common, so I remember that. So first derivative, second derivative, parametrics has dx dt on the bottom, always. The top for the first derivative just has a dy dt. Notice how both of those are being taken derivatives with respect to t, right? For the second derivative, it's d dt again, right? Of my derivative. So I just got to remember, the second derivative, I'm going to get my answer for the first derivative. I'm going to take its derivative again with respect to t. Whatever the answer happens to be, I'm going to do it with respect to t. Okay? So, how can I convince you of this? Well, let me show you a quick example. I know I have an example already set up for us, but let's look at this answer right here that we did before. So our first derivative was negative tangent of t, right? So if I wanted to take the second derivative of this, right, d squared y dx squared, it's by definition d dt of dy dx over dx dt. Okay, that's the definition of the second derivative. Okay, we just figured that out. So, what's d dt of dy dx? So, that's my dy dx, negative tangent of t. So what's the derivative of tangent of t, let's say? Yeah, that'd be secant squared t. There's my numerator, because it's the derivative of my answer. Get it? So my dy dx was already done, so I get that, and I just take a derivative of it, so there it is. Then I divide by dx dt. Well, dx dt, that's sine of t, so the derivative for sine would be cosine of t. Now at this point, I'm not really sure what we can simplify, but this would be 1 over cosine squared t times 1 over cosine of t. So I guess you could simplify it as 1 over cosine cubed t, which would be negative secant cubed of t, and that would be your complete answer once you simplify it. Okay, but it's not as hard as it looks to take the second derivative. Just get your answer for your first, take a derivative of that again with respect to t, then divide by dx dt. All right? So we'll do another example like that. But this is just kind of like a little preview to what you were supposed to do based on that answer right there.
Why do you have to use like this whole equation and not just take a second derivative of -10 t?
It's because you have to, parametric derivatives require you to do top and bottom, right? So when I do the second derivative, you notice in the definition, I have to take a derivative of the top and bottom, right? So in doing so, it just kind of manipulates itself where you still have to take another derivative of x no matter what, right? And it wants you to take a derivative of your answer as well, which is, I guess, right there, dy dx. So it requires you to just take a derivative of your answer still, but because of the way the formula is made and the way the original derivative is made, you still have to divide by dx dt. So we're just following the original definition, but just applying it again. So yeah, you kind of do have to do that. So again, this is, if I could write this down here, d squared y dx squared. This would be your second derivative formula. Again, you can figure it out yourself. Just a lot of people forget what to do at this point right here. They forget that they need to switch those. So then they get a little lost. But if you can remember that, then you don't have to memorize this formula. Just take a derivative again. Okay? So, yeah, I think maybe we'll just show you.
If you didn't, you know how like the reason why we switched them is because of the multiplication, like we're multiplying it so you could like manipulate it?
Yeah.
If you didn't switch it, would you get a different answer?
Well, you'd have to take a derivative of dy dt with respect to x. And y is with respect to t, right? Cosine t. So your derivative would be negative sine of t dx dt. So you'd have, that would be an implicit differentiation. So it becomes more complicated. So yeah, that's why I want to switch it, just to make it easier. So let me show you an example here. So example 2, for the curve given, and they give us x equals to radical t and y equals to 1/4 of t squared minus 4. T is greater than or equal to 0. Find the slope and concavity at the point 2, 3. So find the slope and concavity. So first and second derivative at 2, 3. So obviously we got to take a first derivative, take a second derivative, right? Usually what I do, whenever I do this, since I know something can get a little messy, it might be good for you just to find the first derivative initially without doing too much work, and then the second derivative, like just kind of doing them on the side, and then just plug them in if you want to. So what I mean is, let me find dy dt first. So that would be a 1/4 times 2t, which would be a 1/2 t. Okay, so there's my dy dt. Let me find my dx dt. Well, that's t to the half, so that'd be 1/2 t to the negative half. Okay, so my first derivative is if I just divide those, right? So dy dx is dy dt divided by dx dt. Now dy dt is a 1/2 t, and dx dt is a 1/2 t to the negative half. So if I simplify, the halves will cancel, and t divided by t to the negative half actually becomes addition. That's actually t to the 3/2. Okay, so my first derivative comes out to t to the 3/2. So there's my first derivative. So they ask us to find the slope and concavity at the point 2, 3. Right now we're going to talk about that, okay? So at the point 2, 3, we'll figure it out. But let's first do the second derivative, then we'll do the adaptation of what we need, okay? Because notice, they said at the point 2, 3, that's x, y, but I have a t, so I can't really plug anything in right now, right? So let's do second derivative. So second derivative would be d squared y over dx squared equal to d. I'm just writing down the formula, okay? Dy dx over dx dt. I always find it good to write down formulas over and over again. That way you memorize without really trying. So, okay. So they want me to get dy dx, which is t to the 3 halves. They want me to take the derivative of that with respect to t on top. d dt of t to the 3 halves. So that would be 3 halves t to the negative half. Actually, no, I'm sorry. Positive half. Positive half. So there's my derivative, the top part, d dt of dy dx. Okay? Now the bottom part, we already know dx dt was 1/2 t to the negative half. We got that from before. It's up here. Okay? dx dt, 1/2 t to the negative half. Now I can cancel out those halves, right? 3 halves divided by half, that's a 3. And then t to the half divided by t to the negative half, that's t to the first. So it's 3t. So my second derivative is 3t. All right. At 2, 3, what is t? Because that's what we need. We got to figure out the t value at that point. Okay, so the way we do that is we could just try to figure out what t is using one of the functions that we were given. So the easier function looks like x equal to radical t, right? So x equals to radical t seems to be an easy function. So use x equal to radical t to solve for t. Let x equal to, what's our x value? 2, right? So if x is 2, I get 2 equal to radical t. So I got to square both sides. So that means t has to be 4. So all I have to do is go back to my original answers and plug in a 4 into the values, and I have my answer for what's the slope and what's the concavity. So let's see. dy dx when t equals 4 is 4 to the 3 halves, which is 2 to the third, so that's 8. So my slope is 8 at that point. Now my second derivative, d squared y dx squared when t equals 4, was 3 times t, which is 12. So I'm going to write the following. The slope is 8, and it has and it is, shall I say, and it is concave up. Thank you. At 2, 3. If the second derivative is positive, it's concave up. If it's negative, it's down. So that's what you should get for that problem right there. So this problem right here kind of encapsulates first derivative and second derivative, you know, how to apply it. Can you gain meaning from it, right? What exactly do you do with it and stuff like that. So I'll do one more example, then we'll stop and we'll do arc length tomorrow. It'll be really quick. That means that tomorrow most likely you'll have a good amount of time to kind of work in class on the homework I give you. Okay? Any questions on this one? The finding slope is just, again, based on an equation. Finding your concavity based on another equation, right? Just taking derivatives of your original and then take dx dt. So hopefully it's not too bad. All right. So if you want to, get your calculator. I'm not sure how far you want to go when you draw this. Maybe right now we can kind of play around with it. Let's see. But let me give you another example. So example number 3. So we're going to talk about a prolate cycloid. So that's a type of graph. Okay. So let me write this out. So the prolate cycloid given by, they give us x equal to 2t minus pi sine of t and y equals to 2 minus pi cosine t crosses itself at 0, 2. We're going to find the equation at both, I couldn't read my own writing there, at both tangent lines, or of both tangent lines, sorry. At this point. So if they want us to find equations of tangent lines, then I need a slope and I need a point, right? They already gave me a point, so I basically just need a slope. So I got to take derivatives, and do that. Now, just to give you a picture of what we're looking at, since we're dealing with parametrics and sometimes we're dealing with other type of functions, they can look a little weird at times. So we'll call this, let's see, we'll go with pi here, negative 1, 2, 3, negative pi there. We'll just make normal marks here. And the graph kind of looks like this. Let's see, it's going to be too high, so. Okay, that's what the graph kind of looks like. And it actually comes in this way, from left to right. So there's your directional arrows. Okay, so it's coming in that way and looping around. Notice the point 0,2 is right here. So they're saying this graph will cross itself, and when it crosses itself, you can think of it as having tangent lines, right? 2 different tangent lines. So there's one tangent line that'll cross right there at that point, and then the other one will cross this way. Yeah, it's going to be 2 slopes, but think about it. If they're kind of crossing at the same point and this graph is symmetric, then won't the slope of one and the other just be opposites? Yeah. Right? One will be like, let's say it's positive 2, the other will be negative 2, right? So it kind of makes it easy for us to figure out the slopes. But even if we didn't do that, we'll kind of solve it just to prove it. But we do have 2 different lines, right? So we can call like L and M. Like these are 2 tangent lines that we got to try to figure out. Okay, you could do this without the picture, but the picture might give you an idea of the symmetry of the function. So in order to do this, we're going to have to take a derivative. So let's do that. So dy dx is equal to, that would be dy dt over dx dt. Now dy dt, the derivative of 2 minus pi cosine t is pi sine of t. Because the 2 goes away, the cosine becomes negative sine, so the negatives will go away. And then dx dt, when we do a derivative of that, we get 2 minus pi cosine of t. So that's my first derivative. Okay? So I got to try to figure out what number to plug in. Now, I can't put in 0, 2 because 0, 2 is in terms of x and y, right? So I got to figure out what is the t value at 0, 2. So I'm going to use my functions. Okay? So, I don't know, 0, 2. Let's try using 2. You can use anything to plug it in. It's up to you. But let's try using y equal to 2 minus pi cosine t because it has less stuff in it. So my y value is a 2. So 2 equals 2 minus pi cosine t. So 0 equals negative pi cosine t, or 0 equals to pi cosine of t, or 0 is equal to cosine of t. Well, when are we going to get a 0 for cosine? It's going to happen twice. It's at pi over 2 and 3 pi over 2, right? I'm going to just write it like this. Because that is 3 pi over 2, right? Plus or minus, so one goes up, one goes down. So plus or minus pi over 2. So all I'm going to do is figure out the answers at a pi over 2 and a negative pi over 2. Okay? So dy dx when t equals to pi over 2. Okay? That's going to be pi times sine of pi over 2 divided by 2 minus pi times cosine of pi over 2. Now remember, sine of pi over 2 is 1, so that's going to be pi over 2. Because cosine of pi over 2 is 0, 0 times pi is 0, 2 minus 0 is 2, right? So it's pi over 2. So I'm expecting the other one to be negative pi over 2 just from symmetry, but let's just double check it. So dy dx when t equals to negative pi over 2, that's pi sine of negative pi over 2 divided by 2 minus pi cosine of negative pi over 2. Well, sine of negative pi over 2, or if you want to call it 3 pi over 2, is negative 1. So this would be a negative pi. The bottom is still 0, so 2 minus 0, so that's 2. So those are my two different slopes. So I have two different equations, both with different slopes. So to write the formulas out, let me write the first one. Y minus 2 equals pi over 2 times x minus 0. The other one will be y minus 2 equal to negative pi over 2 times x minus 0. I know I can simplify that, but we'll just leave it like that for now. Remember, in an AP exam, don't simplify unless they tell you. Okay, so they just tell you write an equation of a line. I always recommend point slope because it's usually the easiest one. Don't multiply it out. Don't solve for y unless they say they want it in slope intercept form. Okay, if not, point slope is perfect. I mean, if you do want to solve it, you'd get pi over 2x plus 2 and negative pi over 2x plus 2. I mean, it's not that hard to solve for it, but that's all you need to do. All right, so your homework is on page 727, numbers 5 through 12, 29 to 32, And tomorrow we'll do 49 to 52, but we have to do arc length first.